How about we reverse engineer a personality chip? First thing we need to do is get this orange cap off of that, and then we'll look at what's on the PCB itself, and then based off of what we find, the layout of the PCB, the components inside of it, we'll create a schematic. Take that schematic into some software to formalize it, and then based off of that formalized schematic, we'll create a PCB, and then we'll design that PCB, generate the design files for it, order those PCBs, get them delivered, and then build a personality chip. And if all of those steps go successfully, at the end of this, you'll know how to do this too, how to design your own PCB, and how to perhaps edit the PCB that we create through this process, because I'm going to make that PCB schematic design and the schematic for it publicly available, so anybody can go in and they can screw around with the design, they can put different pictures on it, they could change the layout, do whatever they want with it. The goal here is to educate and make more accessible your ability to create custom personality chips. Alright, so let's begin. That was a grandiose introduction. I have no idea if this is actually going to work. So we need to get this orange cap off of it, and you can see that there is a seam, there are two halves, they have been pressed together over the PCB, and I believe both halves are glued together, so I don't think there's going to be a clean way to get this plastic case off of it, but we'll try. So I'm going to start just taking a screwdriver and wedging it between the seams and see if I can spread it apart at all. No, that corner seems to want to come apart. That side seems to be coming apart very easily. Excellent. What about this side? Oh, that seems to be coming apart too. This might be the first time I actually get both halves of a personality chip apart enough that I'm going to be able to put this back together with glue if I so desire. Oh, look at that. Excellent. That is the first time I have done that. Okay, look at that. There's a little hidden number 3 here. I wonder if different personality chips have different numbers associated with them, or if that's just from the manufacturing of this, the mold for this. Who knows? Let's see. We can see how there are those 4 posts holding the chip in place. The custom personality chip PCB that I have was designed to mimic those 4 holes. And that PCB does not want to come out. Might have to leverage that thing out some more. I don't want to damage the PCB. Oh, something broke there. Hopefully nothing important. I might just be cracking the glue. I'm also probably damaging the PCB itself when I do that. Oh, there we go. There's the number 10. So that's 16. A circle with a 32 on it. Not sure what any of that means. Interesting. So there is our personality chip PCB. And we can make out, hopefully here, some numbers on the chip. P25Q80H. And above that is some text. It's some stylized text. It says Puya on it, which is the manufacturer of this chip. It's the same chip that I have seen in every other personality chip, so there's nothing here surprising about that. Every personality chip I've seen cracked open says revision 1.2. I believe that's referring to the PCB. This G7176-4A, again, I believe is a reference to the PCB. It seems like all of the PCBs have some kind of marking like this that begin with a G. And I believe that symbol there refers to the company that makes it. I'm not certain though. So what do we have? How can we reverse engineer this chip? So we have a memory chip here. That is the P25Q80 from Puya. We have two capacitors. This one's marked C44 and this one is marked C42. And we have a resistor over here marked R33. Further looking at the board, we can see the silkscreen, which is the white stuff, the white text and the markings. On the right here it says VDD, and on the left here it says GND. GND stands for ground, or that's the 0 volt rail is what it's sometimes referred to as. Or if you think of a battery, you have a positive and a negative terminal. Ground would be the equivalent of that negative terminal on the battery. And then VDD would be the equivalent of the positive side of the battery terminal. That is where power will come into the chip. GND stands for ground. VDD, I forget what that stands for. Voltage at the drain, something. It refers to certain types of transistors where the power coming into the transistor comes in through the drain pin. You will also see VCC sometimes instead of VDD. Same idea, different type of transistor, but the C stands for collector, voltage at the collector. So if you see VDD or VCC, you can also think of it as the positive power rail, or the voltage supply, or where the power comes into the circuit. And then we have 5 other pins in the middle that all probably connect to different pins on the chip. So where do we begin? So first, well, let's start with the core of everything, that memory chip there, which we now know is a Puya P25Q80H. And we can look that up on the internet and get a data sheet for that and figure out where all the pins go. I'll get to that in just a little bit. The other thing I want to do is I want to map out where all those pins go, or what I should call the gold fingers at the bottom of the board there. So I think what I'll just do here is I'll draw, well, if I do it this way, 1, 2, 3. This is a terrible drawing. 4, 5, 6, 7. And that represents the bottom of the board. We know that this, already looking at this thing, is VDD, and I'll put a plus symbol for indicating it's like the positive rail. And this is GND. What do those other pins do? Well, before we even crack out a data sheet for this, let's do a little further investigation using a multimeter. Now, there are very expensive multimeters, there are very cheap multimeters. Which one you use for our purposes doesn't really matter, because all I care about is using the continuity mode. Continuity mode means that whenever there is a short between the two probes, it beeps. So if I touch this side of the ground pin or finger and this side, it's just one long strip of copper. There's going to be very little, essentially no resistance, and it beeps. But if I touch the power side, there's no beep, because of course the two are not connected. If they were connected together enough that would cause this to beep, then there's a serious problem with the chip. So we can just go right through the pins real quick here and start mapping them out. One thing to note as I start mapping these out is if we look closely, if this thing wants to focus, there is a small dot on the chip right there, right where the probe tip is, that identifies this pin that I'm now touching with the probe as pin 1, and the standard way for counting pins on a chip like this would be 1, 2, 3, 4. Go across from it 4, 5, 6, 7, 8. Okay, so pin 1, 2, 3, 4. Pin 5 is up here. Pin 6, pin 7, and pin 8. Okay. So I want to see where those pins connect to over onto these gold fingers, get an idea of how things are laid out. So I'm going to zoom in here, and with my probe I'm going to put one probe on the gold finger here, and then I'm just going to start touching different pins and see if I hear a beep. Actually, I should start with the ground. Let's find the ground pin. Looks like pin 4. Pin 4 is the ground pin. So I'm just going to write a number over my little schematic here. Not a schematic, my drawing of the pin number. So I'll put pin numbers over all of these. So let's go back in here and map these all out. Let's do power. Where is power going to be? Both pins 7 and 8 go to power. So I'm going to do 7 and 8 like that. And we'll just keep on probing and map this out. Okay, so we've got a basic pin out now. We know where the different pins of the chip go. Now there is a couple of curious things. The first one is, why is power coming in here and also here? The other interesting thing, why are pins 7 and 8 of the chip itself connected together? These are questions we want to have in our mind before we go looking at the data sheet. The data sheet will answer everything. The third question is, where's pin 3? Pin 3 on the chip is not represented anywhere here. So pin 3 on the chip doesn't connect to any of the gold fingers. Again, interesting. So now we should probably track down the data sheet for this chip. Actually, before I even do that, let's make a note here. Let's draw that chip. 1, 2, 3, 4 on each side. Put a circle up here to indicate where pin 1 is. And we know that pin 4 goes to ground. And we know that pin 8 and 7 go to VDD. So already we have some elements of the schematic. Let's look at the data sheet for more. And I know that we have a resistor and 2 capacitors that we also need to put in this circuit somewhere. We'll get to that. But for now we have some questions about where's pin 3 on this, and why are 7 and 8 connected together? What's going on there? So let's look at the data sheet and see if that has the answers to our questions. Alright, so if we go online and type this into a search engine, we should find this, which is the data sheet for that memory chip. And we can see it's a serial flash memory chip. It's an 8 megabit one. Those are megabits. There are 8 bits in a byte. So if you divide this 8 by 1, if you divide this 8 by 8, you'll get 1 megabyte. 8 megabits, 1 megabyte on that chip. Or about 1 minute's worth of an MP3. And a few pages into that data sheet, you'll find this, which is the pinout for the chip. We know now what those pins are for. We can see pin 4 is ground, just like we found when we were testing it with the multimeter. Pin 8 definitely connects to, well, in this case they're calling it VCC. Also in the datasheet is a description of what each pin is for, so we can take a look at that and figure out how all of this is connected. So let's go pin by pin, and we'll mark that out on our little diagram here. So pin 1 is the chip select pin. Basically what that means is when this pin is active, the chip will respond. So if you send it a command to spit out some data from some specific address in the chip, only if this chip is activated through the chip select pin, if the chip has been selected, will the chip respond. Otherwise it'll just ignore the request and it'll just sit there idle and not do anything. The symbol says CS, and then it's followed by a hash or pound symbol, whatever you want to call it. That hash symbol indicates that the pin is active when it's low. So you have your positive power rail, your negative power rail, we'll call that VCC and ground. If pin 1 is connected to ground when it's low, chip select is enabled. So we'll come over here and do CS like that. And we saw pin 1 was connected over here, so we know that when power is applied to this pin of your personality chip, that's the Droid, or the microcontroller of the Droid, telling the chip, hey, you're on, start doing stuff. Pin 2 is SO, which is the serial output. That, when you ask the chip to spit out some data, the data is going to come out of that pin. Pin 3 is the WP pin, or write protect, and we can see it has a pound symbol associated with it, which means that the write protect is only enabled when the write protect pin is connected to ground. Now this sort of answers the question, why is there no pin 3 here? The microcontroller in the Droid doesn't care about setting the write protect pin, because it's not going to be it will not ever be writing to the chip. It will only ever be reading from the chip. So that write protect is probably connected to ground on the PCB itself, and so we'll have to go and double check that in a little bit. But that's probably why there is no write protect on the gold fingers of the personality chip. Pin 4 is ground. Pin 5, serial input. So this is where the request from the microcontroller in the Droid saying, hey, I want you to give me the data for this audio track, and it will send that request through that serial input pin. Pin 6 is the serial clock pin. Every time the serial clock pin will transition between the voltage VDD and the voltage at ground, so between 3.3 volts and ground, it'll be oscillating between those two states. When the transition occurs from high to low or from low to high, that tells the chip it's time to either put data out of the serial output or read data from the serial input pin. So whatever is driving the clock signal is what drives the speed at which information is read out of or sent into the chip. The microcontroller will drive the clock. And it could be several thousands, hundreds of thousands of times a second, maybe even a million times a second. It all depends on what the programmers who wrote the code for the Droid decided to use. All right, pin 7. Pin 7 is the hold pin, and it also has a hash mark associated with it, meaning that it's active low. And it's to pause the device without deselecting the device. So in other words, it just tells the device to hold on outputting any data. Stay where you are, remember your position, but stop for a moment, I got to do something else. And it's active low. So I'll write that over here. And now we sort of have an understanding of why this hold pin is connected to VDD. It's permanently disabled. This feature is permanently disabled on that PCB. So pin 7 isn't by itself being sent to any of these gold fingers. The Droid is never using this hold feature, so it's permanently disabled by connecting it to VDD. That is why we saw pins 7 and 8 connected there, which means a new question is, what the heck is this middle finger for? Well, we'll figure that out in a moment. And then pin 8 is VCC, which we could also put this in parentheses. VDD, VCC, they're the same thing. Alright, so with the data sheet, we now understand how this pin is set up, why we have pin 7 and 8 connected together like that. We understand, we have a pretty good idea why pin 3 isn't here. It's probably being pulled down to ground somewhere on the board and never getting to these fingers here. And we'll double check that in a minute. We understand the connections to the fingers. We want to go back to that PCB real quick, and we want to look at those the resistor and 2 capacitors and figure out where they are, so we can finish our little schematic here. So if we look in real close here, we don't even need the multimeter for this. This is another way we can look at how the board is connected. You'll notice there's a dark green area and a light green area. The green is solder mask. It's like a, you can think of it as like a nail polish. And the idea is wherever the solder mask is, solder won't stick to the copper. But then wherever copper is exposed, like these fingers down here, solder will flow. So they put the solder mask down so that way when they start soldering the pins to the board, there are these little gaps between pins, so that way the solder will more likely flow on just the one pin you're shooting for and not try to bridge the pins out. Underneath the solder mask is copper and bare board. The copper shows up as a light green and the bare board shows up as a dark green. So wherever you see light green, it's essentially like a wire connecting components on the board together. These are usually called traces. And we can see, for example, here's your VDD pin, and you can see there's a trace that comes up through here, does a little turn, and comes right up to this capacitor. And then on the other side of the capacitor, we can see it comes out to ground. So we have a capacitor between power and ground. So we can mark that on our little schematic here. Very simple. We could say, how do I want to draw this? I think I'm going to draw this over here. So we have our ground symbol, we have our VDD symbol, and in the middle we have a capacitor. And that capacitor is got a mark on it, right? C42. C42. Now we have another capacitor here, C44, and if we again look at the trace, we can see we have a trace coming out of what looks like pin 6 to the capacitor, and then the capacitor again is connected to ground just like the other one. So coming out of pin 6 we have another capacitor connected to ground, and that is C44. One thing that will help you to see the traces is if you take a flashlight, turn it on, and put the board over the flashlight, you can see the traces much more clearly through the board. You can see there is a trace coming out of pin 6, and then how it goes down, takes a left-hand turn into a via. We'll talk about vias in a moment. It might look like to you that that trace coming out of pin 6 isn't going all the way to the capacitor. That is because of the white silk screen that is blocking the light coming through it. So, or is being reflected to us. It looks like there's a break there. It's not. It's just the silk screen sort of covering that trace up. Now we know the clock symbol, or the clock goes to what is that, pin 6? So we can see that the clock should go to the finger just to the right of the middle. And we can confirm that real quick. Visually, without the multimeter, we can see we're coming out of pin 6 here to that capacitor we were looking at, but then we also see that there is a via. All these little holes you see here are vias. What they do is they connect the copper on the top side with the copper on the bottom side. They're like a wire going through the PCB from one side to the other. So we can see we have a hole here, and if we go through the middle of the hole towards the middle of the board, we're going to encounter a via. That's the via we're looking for. So I'm going to flip this over. We're going to start in the middle of the hole here. Stop focusing on the drawing. We're going to come across past the 32, and there's our via, and it comes down to the pin just to the right of the middle finger, or the finger just to the right of the middle finger. And then you can see here's another via way over here. Well, let's see that. We have a via right on the top of the middle pin, and then just above it, and to the left on this side, it'll be to the right when we flip this over, is another via. Let's see where that goes. Here's the middle via for the middle finger, and then just to the right of it, there's that via, and it's coming down again to connect to the finger to the right of the middle. So that's how these two fingers are connected to each other to the clock pin. And you'll notice that the layout here of all these pins mirror. The front mirrors the back side. So this is the ground on the left. The ground is on the right, on the left when you flip it over. Power is on the right. Flip it over. Power is on the right. The clock is to the right of the middle over on this side. And the clock is to the right of the middle on this side. So they're mirroring each other. This is something we'll have to keep in mind when we start designing the PCB itself. Okay, so capacitor, what's left? We have a resistor, R33. Where does that go? Let's grab that flashlight and take a look at the traces here. See what we can see. And it looks like R33 is connected to pin 3, and then it comes off of pin 3, and it looks like it's connected to ground. So how do I know that that's ground? Well, you can see, if this thing wants to focus, here's your ground pin, and you can see it connects to this big copper area that comes up over here, up across the top, with all these extra vias that are connecting the ground plane of the front side of the PCB to the back side ground plane of the PCB. We can see it comes over here to this side, down around behind this resistor. So we have a resistor coming out of pin 3, or pin 3 to a resistor to ground. So pin 3, that's the right protect pin. We have a resistor, which I'll draw like a big box, and that comes down to ground, and that is resistor, focus, resistor 33, and its value is 01C. 01C, what does that mean? I don't know. Now we could look that up online. It should be a standard resistor code, or we bring in the multimeter again, but this time we actually want it to measure resistance instead of just beeping. And then I put this across the resistor like so. And that is measuring 10 kilo ohms. So that is a 10 kilo ohm resistor. So now we've got a couple of capacitors, a resistor. We've got our schematic more or less done. The pins here that we don't have connected are just going directly to the gold fingers on the board. But it would help if we knew the capacitance of C44 and C42 if we're going to replicate this. Here comes the fun part. How do we know what those values are? Now, this multimeter does have a capacitance feature. There's just one problem. I'm going to measure C42 here. In fact, I can just go between ground and power like this. You're going to see the multimeter is going to have a really difficult time here. And the reason is the power that the multimeter is putting out to measure the capacitance is also going into the chip. The chip is gobbling up that electricity and screwing up the reading of the capacitor. The same thing is going to happen over here with the capacitor on the clock pin. So, again, how the heck do we figure out the values of those components? And the short answer is you could guess. For example, since we know that the capacitors between power and ground, that's going to be a bypass or decoupling capacitor. It's a very common technique. The idea is it acts like a little reservoir of electricity, so that when there are little fluctuations on the power rail coming into the chip, the capacitor, which acts like a reservoir, it will put out a little extra electricity when the voltage dips below a certain value, and then it'll start, when the voltage comes back up, it'll start to refill itself. You can also think of it as like a little tiny battery, and they call them decoupling or bypass capacitors because they're decoupling the chip from the rest of the power rail. The other capacitor, though, on the clock pin is odd. Let's see, this connects out to the gold fingers, and maybe this is something I should do here. Just put these little sort of blocky arrows to show you what connects to the gold fingers. 1, 2, 3, 4, yep. And I have never seen a capacitor on a clock line before. That's odd. I'm guessing it's there to either as a filter to filter out weird transients coming into that line. Maybe that's what it's for. I'm not really sure, but we'll need to figure out what the values are. And we could guess, as I said, a decoupling capacitor, 10 nanofarad, 100 nanofarad, a microfarad. These are all normal values for decoupling capacitors. The clock capacitor, not real sure. So I want answers, and you do too. So really what I'm going to have to do is I'm going to have to desolder those two and measure them out of circuit. So I'll get set up for that. Okay, so my plan here is I'm going to apply some solder to either side of the capacitor I want to remove, because that should help. And then I'll try and apply a big blob of solder and hopefully get the whole thing out in one go. Okay. How am I going to do this? I think I want to apply a bigger blob of solder. There we go. It's burning, it's burning. Get it off of the soldering iron. Okay. Put that off to the side for the moment. There is the capacitor, this tiny little thing here. I'm going to clean it up real quick. Oh, shh. All right, you know what? Yeah. It's gone. It's gone. It's on the floor, and I don't know where it is. It's gone. I have always said that this is a 5 picofarad cap. Let's see if I'm right. Alright, so it's probably more like a 15 picofarad. Time for the specialized meter. Okay. This is an LCR meter with tweezer tips. Let's see what it thinks we have here. (10 picofarad). So you can get the idea pretty quickly here that this is a very small capacitor. (10 picofarad). Now I'm going to put that back on, and I'm going to need to go find a 100 nanofarad cap to throw in place of the one that I have lost. Okay, crisis averted. Capacitors are back in, and I think we're done with looking at this. For now, we have a schematic. We know what components go where. Dimensions for the PCB we'll figure out when we get to actually designing the PCB, but we'll want to take note, for example, how the gold fingers are staggered. You notice even the power pin, or finger, is a little bit farther above the edge of the PCB than the ground pin. Onward and upward.